Alright, so first off, what is the arithmetic logic unit or ALU for short? So the arithmetic logic unit is also known as the ALU, and it's one of the most main components inside the CPU. It is often described as the part of the that does the actual work of the computer. The ALU is responsible for handling all the mathematical operations, such as making the simple decision based on the command it receives. In a computer system, the role of the ALU is very important. It because it performs the arithmetic operations such as addition, subtraction, multiplication, and division. So aside from the calculations, the ALU can also compare values and check the conditions which are needed when the program is running and making its decision. The ALU is also important because it allows the computer to properly process data and execute the instructions correctly. Without the ALU, the computer would not be able to perform calculations or make a logical decision, which means that the program itself would not be able to produce the correct results. So in short, the ALU it plays a big role in making sure that the CPU can function properly and efficiently. Next step is the program flow in a computer system. So the program flow describes on how a computer follows the instruction in a specific order while a program is running, and it also shows the instruction and data that moves inside the system until the task is fully completed. So basically, it explains on how the computer knows what to do first, next, and last. So when the program is opened, the instructions are first stored in the memory. The CPU then fetches these instructions and one at a time. After fetching it, the CPU decodes each instructions to understand what needed to be done, and it prepares the instruction for the execution. So the ALU plays an important role in the program flow. If an instruction requires a calculation or comparison, the CPU will send that instruction to the ALU. Then the ALU itself will process the operations such as arithmetic or logical comparisons, and then send out the result back to the CPU. The CPU then uses this result to move on to the next instruction. So overall, the program flow is important because it ensures the instructions are executed in a correct order, allowing the computer to run the program smoothly and correctly. Then the next part is the overview of ALU functions. So the arithmetic logic in unit in ALU is responsible for handling both calculations and logical operations. It plays a major role in processing data and executing instructions in a computer system. Whenever a program needs to work with the numbers or make a decisions, the ALU is always involved within it. The main functions of the ALU is one of the main functions is performing the arithmetic operations. These include addition, subtraction, multiplication, and division, just like in my earlier reports. These operations are used when a program needs to calculate values or produce results, such as in maths problems or data processing. Next aside is the logical and comparison functions. Aside from the arithmetic tasks, the ALU also performs the logical and comparison functions. It can handle the logical operations like AND, OR, and NOT. The ALU also compares the values to check the conditions, which helps the computer to decide what action needs to take while the next program is running. So overall, the ALU is important because it allows the computer to process data correctly and make the decisions based on the instructions given. And lastly, from my part, which is the arithmetic operations of the ALU. The arithmetic logic unit ALU is the part of the CPU that performs the basic mathematical operations. It is responsible for handling calculations needed by the program during the execution. The ALU performs the arithmetic operations such as addition, subtraction, multiplication, and division. As for these operations are important because they allow the programs to com- compute values and produce correct results during its execution. And
So the logic operations of the ALU or ALU. The logic operations work on binary values 0 and 1 and are essentials for decision making in computer systems. So here are the basic logic operations. First is the AND operation. The AND operation produces an output of 1 only when both inputs are 1. If any input is 0, the result is 0. This operation is commonly used when multiple conditions must be true at the same time, such as checking if a user is logged in and has permissions. The next one is OR operation. The OR operation produces an output of 1 if at least one of the inputs is 1. It only outputs 0 when both inputs are 0. This is useful when a system needs to check if any one condition is satisfied. Next is the NOT operation. The NOT operation works by inverting the input value if the input is 1. The output becomes 0, and if the input is 0, the output becomes 1. The operation is often used for negation, such as reversing a condition or toggling a state. So the last one is the exclusive OR operation. The exclusive OR operation produces an output of 1 only when two inputs are different. If both inputs are the same, the output is 0. So exclusive OR is commonly used in error detection, data comparison, and simple encryption techniques. So the next one is the importance of the arithmetic logic unit or ALU operations. So these ALU operations lies in the fact that they allow a computer to process data and make decisions. Every calculations and logical comparison inside a computer depends on the ALU. So ALU operations are essential for decision making in programs, especially in conditional statements like if-else and loops. They allow the computer to compare values, check conditions, and control the flow of execution. These operations are also important for data processing, including numerical comparisons and bit-level operations. Through ALU operations, the CPU can decide the next instructions to execute, making the system efficient and reliable. So, overall, ALU operations form the foundation of how computers function logically and accurately. So, what is the control unit? The control unit is an important part of the CPU that controls and coordinates all the activities of the computer. So its main functions are to fetch instructions from memory and then decode them and then send control signals to other components like the ALU and memory. It also controls the timing and sequence of the operations, and the control unit does not perform calculations by itself. Instead, it tells the ALU what operation to perform, and the ALU carries it out. So for example, if the instruction is to add two numbers, and the control units will tell the ALU to perform the addition operation, and the ALU produces the results. So the control unit and the arithmetic logic unit interaction. So these two work together to carry out the instructions within the CPU. The control unit fetches and decodes instructions from memory and sends control signals to the ALU. Then the ALU performs the necessary arithmetic or logical operations on the data. Then the control unit manages when and how the ALU operates to ensure that each instruction is executed properly. The diagram shows this interaction with the CU, ALU, and memory communicating to process inputs and produce the outputs.
For our simulation, I'll be using a software called Logisim. So now let's build our ALU starting with the arithmetic operation. So first, let's set the input values for our ALU. So using this pin, let's set its data bits into 8. I will label this as our input A, and then let's duplicate and change it to B. So now we have 2 input values. So this second pin represents a 8 bits. Now let's add the arithmetic components that will perform the operation. So we have here the adder. So this one will handle the addition operations. Then the subtractor, which is for the subtraction, multiplier for multiplication, and then the divider for division. So now I'll connect the inputs A and B to each arithmetic operation. So let's just say let's change the facing to south for it to be organized. So now let's connect each of the inputs to our operations. So this allows the same input values to use all the operations. So next, I add the multiplexer to select which arithmetic operation will be used. So this is the multiplexer. So the multiplexer allows only one operation results to be passed at a time based on the selected control value. So now let's just change the selected bits to just 2. So, and then the data bits, of course, it's the 8. And then let's just say it. And then now let's connect it to our operations. And then let's add a pin and set it to north, and the data bits same as the multiplexer, which is 2. So this will we will adjust this based on what operation we want to operate. So that's it. And lastly is the output. So it is incompatible. So let's just set this to our dedicated bits, which is 8. So our arithmetic ALU is now set. Now that our arithmetic ALU is ready, let's start the simulation and see how the output changes when we modify the inputs. So first, select the addition. So it is already selected in this multiplexer. And then let's change the inputs. So A, let's set it to 8, which is 1 0 0 0, and then B to, let's say, 5 1 0 1. So as you can see, it already changed the output here, which turns into 1 1 0 1, which is equivalent to 13. So 8 plus 5 is 13. That's correct. So now let's just try to tweak this B into 7. So as you can see, it changes the output 1 to 1 1 1 1, which is equivalent to 15. So let's reset this And now let's try the input 1. So input 1 by changing the selector. So 0, 1 is equivalent to input 1, which is our subtraction. So let's try it by changing our inputs. So A, let's set A into 15, which is 1, 1, 1, and then B to 6, which is 1, 1, 0. As you can see, it changes the output into 1, 0, 0, 1, which is equivalent to 9. So this 15 minus 6 is equivalent to 1, 0, 0, 1 or 9. So by changing the B, let's try 5. So 15 minus 5 is 1, 0, 1, 0, which is equivalent to 10. Now let's try the multiplication by changing the selector into this 1, 0, which is equivalent to input 2. So let's set the A into, let's say, 4, which is 1, 0, 0, and then B to 3, which is 1, 1. So as you can see, change the output to 1, 1, 0, 0, which is equivalent to 12. So it is correct that 4 times 3 is equal to 12. So let's change the B into 5, which is 1, 0, 1. So as you can see, we change the output into 1, 0, 1, 0, 0, which is equivalent to 20. So it is correct that 4 times 5 is equal to 20. Now let's just reset and try the division. So by changing the selector into 3, we select the division. And then let's set A into, say, 16. So 16 is equivalent to 1, 0, 0, 0, 0 in binary, and then let's set B into 4, which is 1, 0, 0. So as you can see, it changed the output into 1, 0, 0 also, because 16 divided by 4 is equal to 4, which is 1, 0, 0. And then let's change it to, let's say, 2. So 1, 0 is good, it's binary, and it changes the output into 1, 0, 0, 0, which is equivalent to 8. So it is correct. 16 divided by 2 is equal to 8. So that's it for the arithmetic ALU operation. So as you can see, it changes the output based on the input values, and then also the selected operation. So it shows the real-time process like in a real CPU. Now let's build our ALU, starting with the logic operation. So let's just copy these inputs, and then the input B also, and then now let's add the logic components that will perform the operation, which is in the logic gates folder. So as you can see, we have the AND gate, the OR gate, also use the NAND gate, and the NOR gate. So let's just change the number of inputs into 2 for each component. And then now let's connect the inputs A and B to each logic operation. So for B is By the way, let's just try to change the data bits of each gate into 8 so it is compatible with our inputs. 8 and this is 8, and now let's try to connect it. Edge of it for A. Then let's add multiplexer, so let's just copy paste this one and then connect it to our multiplexer. Then let's copy this also, selector, and then the output. Right, so as you can see, we already set our ALU for logic operation. So now let's try to simulate the logic unit of our ALU. So I'll demonstrate the AND, OR, NOR, and NAND operations. So let's first set the values for our inputs. So let's just say our input A is 1 0 1 0 1 0 1 0, and then our input B is 1 0 0 0 1 0 0 0. So first let's select the AND operation. So it's already selected here or on our multiplexer 0, which is connected to our AND operation. So with the input A and B, the output is 1 0 0 0 and 1 0 0 0. So this is because AND outputs 1 only when both corresponding bits are 1. So let's just try to change our input on B, which is 1. So 1 1 1 1 0 0 0 0. So as you can see, the output is 1 0 1 0 0 0 0. So it corresponds with the inputs in our input A. So now let's try OR operation. So by changing our selection here, we select the OR operation. So with the input A and B, which is 1 0 1 0 1 0 1 0 and 1 1 1 1 0 0 0 0, so it changes into 1 1 1 1 1 0 1 0. So our inputs 1 if either bit is 1. So let's just try to change the value of B to, let's say, this. So it automatically change our output into 1 0 1 0 1 1 1 1. So now let's try the NAND, and then yeah. So as you can see in this, with the input of the A and B, our output is 1 1 1 1 0 1 0 1. So NAND is the NAT of the NAND, the AND. So it outputs 0 only when both bits are 1. So in our inputs, there is only a place where they both inputs 1. So in the second and then in the fifth. So as you can see, this is the output for that. Now let's try the NOR operation. So let's just say, let's try to change the inputs of B to 0001 to 0001. So this is the output for that inputs 01, 000, 100. So as you can see, NOR or NOR operation is the NOT of OR. So it outputs 0 if either bit is 1. So in conclusion, our discussion has shown how the arithmetic logic unit or the ELU serves as the heart of the computer processor. We explored both its arithmetic operations like addition, subtraction, multiplication, and division, and its logic operation including AND, OR, NOR, and NAND. So we saw how the ELU process inputs data according to instructions and how the control unit coordinates which operations perform at any given time. So through our simulation, we demonstrated the real-time processing of both arithmetic and logic operations, showing how changing inputs and operation selections immediately updates the output. So overall, this project highlights the critical role of the ELU, including the instruction performed, calculations, and supporting the overall program flow of the computer system. So it clearly illustrates how input control signals and processing work together to produce the results essential for computing tasks.